In December 2021, a rocket launched from a jungle in French Guiana, carrying the most expensive, most complex, most carefully engineered scientific instrument humanity has ever built. It had taken 30 years to design, 10,000 people to construct, $10 billion to fund. And it had been delayed so many times by technical problems, budget overruns, a tear in the sunshield, a botched launch preparation that nearly ended everything, that the scientists who had dedicated their careers to it had started to wonder in their quieter moments whether it would ever actually fly. It flew. And what it found, in the months and years that followed, has done something that very few scientific instruments in history have managed to do. It has forced us to rewrite what we thought we knew about the beginning of everything. The James Webb Space Telescope has detected the oldest light ever seen. Not just old light, not just impressively distant light. Light from a time so close to the very beginning of the universe. From galaxies that formed so early, so fast, so large, that our best models of how the universe works cannot fully explain their existence. Light that left its source when the universe was less than 300 million years old, less than 2% of its current age. Light that has been traveling through an expanding universe for over 13 billion years, redshifting as it went. Its wavelength stretching from ultraviolet to infrared, from the blue end of the spectrum to the invisible, carried on a journey across the entire depth of the observable cosmos. And it landed finally on a gold-coated hexagonal mirror floating 1.5 million kilometers from Earth. And what it showed us has changed cosmology. In this video, we are going to go on that journey. We are going to start with light itself, what it is, what happens to it over cosmic distances, and why the oldest light is the most scientifically precious thing in the universe. We are going to go through the history of how we learned to see the early universe, the revolutionary instrument that finally let us see it clearly, and the specific discoveries that have upended decades of theory. And then we are going to ask the question that the astronomers themselves are now asking in their papers and conferences and late-night arguments with each other. If these early galaxies exist, if they formed this fast, if they are this massive, what does that mean about the Big Bang? About the laws of physics? About what we fundamentally misunderstood? The oldest light in the universe is not just old, it is a message. And the message is, you were wrong about something important. Let's find out what. Chapter 1. What light is, and what it carries. Before we can understand what the James Webb Space Telescope found, we need to understand what light actually is. Not the pop science version, the real version. Because the physics of light is not just background material, it is the entire mechanism by which we know anything at all about the universe beyond our solar system. Light is an electromagnetic wave. It is a self-propagating oscillation of electric and magnetic fields, traveling through space at 299,792 kilometers per second. The universal speed limit, the fastest anything, can move through the fabric of space-time. It requires no medium to travel through. It crosses the vacuum of space without losing energy, without slowing down, without needing anything to carry it. A photon, a single particle of light, emitted from a source 13 billion light-years away, will travel for 13 billion years, across expanding, cooling, structuring space, and arrive at your eye or your telescope with its information intact. This is extraordinary when you sit with it. Light is essentially a message in a bottle, except the bottle is indestructible. The ocean it crosses is 13 billion light years deep, and the message it carries is not text, but physics. The temperature of the source, its chemical composition, its velocity, its distance, how much time has passed since it was sent. The key to reading that message is the spectrum. When you look at ordinary white light through a prism, it fans out into a rainbow: red, orange, yellow, green, blue, violet. Each color corresponds to a different wavelength of light. Red light has a longer wavelength, around 700 nanometers. Violet light has a shorter wavelength, around 380 nanometers. The full range of colors visible to the human eye, what we call visible light, occupies a narrow band of the electromagnetic spectrum, from about 380 to 700 nanometers. But the electromagnetic spectrum extends far beyond what our eyes can detect. Shorter wavelengths than violet, ultraviolet, X-rays, gamma rays, longer wavelengths than red, infrared, microwaves, radio waves. All of these are light. All of them are photons. The only difference is wavelength, and wavelength determines the energy of the photon and the way it interacts with matter. Here's the part that matters for understanding the oldest light in the universe. Every element in the periodic table interacts with light in a characteristic way. When an atom absorbs a photon, the photon's energy kicks an electron to a higher energy state within the atom. When the electron drops back down, it releases a photon of a specific, precise wavelength, determined by the energy difference between the electron states. This process creates what's called a spectral line, a specific wavelength of light that a particular element either emits or absorbs with particular intensity. Hydrogen, the most abundant element in the universe, has spectral lines at very specific wavelengths. The most prominent series, the Lyman series, falls in the ultraviolet. Oxygen has its own lines. Carbon has its own. Every element is a unique barcode of spectral lines, a signature that identifies it wherever it appears in the universe. This is how we know what stars and galaxies are made of. We look at the light they emit, spread it into a spectrum, and read the barcodes. We can tell the temperature of a stellar surface, the chemical composition of an atmosphere, the presence of specific molecules in a gas cloud, all from the wavelengths of light a source emits or absorbs. And here is where it gets crucial for the story of the oldest light. When a light source is moving away from you, the light it emits gets stretched. Each successive crest of the electromagnetic wave is emitted from a slightly greater distance, so the distance between crests, the wavelength, increases. The light shifts toward the red end of the spectrum. This is called a redshift. In our everyday world, you hear the acoustic equivalent of this with sound waves, the Doppler effect, the way a passing ambulance's siren drops in pitch as it moves away from you. For light, the same principle applies. A source moving away emits light that arrives at a longer wavelength, redder than the source wavelength. Now here is the fact that underpins all of modern cosmology. Every distant galaxy in the universe is red-shifted, not because they're all coincidentally fleeing from us, but because the space between us and them is expanding. The universe is getting bigger. The fabric of space-time is stretching, and as it stretches, the light traveling through it gets stretched along with it. The farther away a galaxy is, the more space there is between us and it, the more that space has expanded while the light was in transit, and the more redshifted the light is when it arrives. Astronomers quantify this with a number called the redshift parameter, written as z. A redshift of z equals 0 means no redshift at all. The source is right next to us. A redshift of z equals 1 means the wavelength of the light has doubled, each wavelength stretched to twice its original length by cosmic expansion. A redshift of z equals 6 means the wavelength is 7 times longer than it was emitted. At z equals 13, the wavelength is 14 times longer. Before we go further, here is something that trips people up and is worth pausing on. When astronomers say a galaxy is at redshift z equals 13, they don't mean it is 13 billion light years away. They mean something more complicated. Because while the light was traveling toward us, the universe was expanding. The space between us and the galaxy was stretching. A galaxy that emitted light when the universe was 320 million years old is not 320 million light years from us today. It is much, much further, roughly 33 billion light years, because the expansion of space has carried it to that distance in the 13+ billion years since the light departed. This distinction matters because it tells you something important about the nature of the oldest light. It has not just traveled a long distance. It has traveled through an expanding medium that stretched it, changed it, the entire way. Every meter of space it crossed was itself expanding as the photon crossed it. The photon we detect today carries within its redshift the entire history of cosmic expansion from the moment it was emitted to the moment it arrived. Reading the redshift of a distant galaxy is not just reading its distance. It's reading the history of the universe written into a single number. That number encodes, if you know how to decode it, the age of the universe when the galaxy formed, how much space has expanded since then, and how much time has passed. The spectrum of a single distant galaxy is a document about the entire history of cosmic expansion. And here is why this matters for seeing the oldest light, the very early universe. The universe of the first few 100 million years was full of young galaxies emitting light in the ultraviolet. Those galaxies are now at redshifts of z equals 10, 12, 15. The ultraviolet light they emitted has been stretched by the expansion of the universe over more than 13 billion years to wavelengths in the near infrared, wavelengths between about 1 and 5 micrometers. The Hubble Space Telescope, the most celebrated observatory ever launched, could not see infrared light beyond about 1.7 micrometers. It was fundamentally, physically incapable of detecting the most redshifted light from the earliest galaxies. It could peer back to about z equals 11 or 12 at the very limit of its sensitivity, glimpsing the universe at about 400 million years of age. The James Webb Space Telescope was designed specifically to see further. It was designed to detect infrared light out to 28 micrometers, deep into the infrared, well beyond anything Hubble could access. It was designed explicitly to see the light from the first galaxies in the universe, to push through the redshift barrier and reach the cosmic dawn. It was designed to find the oldest light ever seen, and it did. Chapter 2: The first light. What was there before the stars? To understand why the oldest detected light is so significant, you need to understand what the universe looked like before it was emitted. Because the context makes the discovery and makes the discoveries that followed it genuinely shocking. Go back, way back. 13.8 billion years ago, the universe began in a state of incomprehensible density and temperature. The Big Bang was not an explosion in space, it was an explosion of space itself. Space-time did not exist before it. There was no before in any meaningful sense. The universe simply began from a state of essentially infinite density and temperature and expanded. In the first fraction of a second, fractions of a second so small, they have no analogy in human experience. The universe was a seething plasma of quarks and gluons and leptons, so hot that not even protons and neutrons could form. As the universe expanded, it cooled. By about 1 second after the Big Bang, protons and neutrons had formed. By about 3 minutes, nuclear fusion began. Hydrogen nuclei fused into helium and trace amounts of lithium. This is Big Bang nucleosynthesis, the forge of the lightest elements. But the universe was still opaque. The plasma of protons and electrons was so dense that photons, particles of light, could not travel more than a tiny distance before being scattered by a charged particle. The universe was a fog. Light could not travel freely. This continued for 380,000 years. Then something extraordinary happened. The universe cooled to about 3,000 Kelvin, roughly the temperature of a cool star's surface. At this temperature, electrons could combine with protons to form neutral hydrogen atoms. For the first time, matter was neutral. And neutral hydrogen does not scatter photons the way charged particles do. Suddenly, abruptly, in astronomical terms, the fog cleared. Photons that had been trapped in the plasma were free to travel. They have been traveling ever since. That light from 380,000 years after the Big Bang, released when the fog cleared, when the universe first became transparent, is still detectable today. It has been stretched by 13.8 billion years of cosmic expansion from a temperature of 3,000 Kelvin down to about 2.725 Kelvin above absolute zero. It now fills the sky uniformly in every direction, in the microwave part of the spectrum. We call it the cosmic microwave background, and it is the oldest light we can detect with any electromagnetic instrument. A perfect thermal glow from the moment the universe first cleared. But between the CMB, 380,000 years after the Big Bang, and the first stars, there is a period that cosmologists call the Dark Ages. No stars, no galaxies, no light sources of any kind. Just vast, dark clouds of hydrogen and helium gas, the raw material of everything that would follow, drifting through the expanding universe, slowly falling together under gravity into the first gravitational knots. For perhaps 100 to 200 million years, the universe was dark, genuinely, completely dark. Not even starlight to illuminate the hydrogen clouds. The universe had cleared, the CMB photons were flying, but nothing had yet ignited. It was cold and dark and silent, a universe full of potential and devoid of light. And the darkness was not uniform. The tiny temperature fluctuations in the CMB, those 1 part in 100,000 variations in the thermal glow, were the seeds of everything to come. Slightly denser regions attracted more matter gravitationally. dark matter halos, invisible clumps of gravitating material, formed first because dark matter does not interact with light and could therefore start collapsing earlier than ordinary matter, even while the universe was still opaque. Ordinary matter fell into these dark matter gravitational wells once the universe cleared. The denser regions grew denser, the emptier regions grew emptier. Over millions of years, the first knots of gas, compressed by gravity into dense filaments and clumps, grew hot enough in their centers to ignite nuclear fusion. The first stars switched on. This moment has a name. Cosmologists call it cosmic dawn. The first stars were nothing like the sun. They were giants, massively, almost incomprehensibly more massive than modern stars. Hundreds, perhaps thousands of times the mass of our sun. The reason they were so massive is that the primordial gas from which they formed contained no heavy elements at all. No carbon, no oxygen, no elements heavier than lithium, because all of that would have to wait to be forged in stellar interiors. Without heavy elements to radiate away heat efficiently during the collapse of a gas cloud, the cloud couldn't fragment into smaller pieces the way modern star-forming clouds do. Instead, the collapse continued until an enormous single object formed, a star of perhaps 100 to 1,000 solar masses, burning at a ferocious temperature, producing radiation at an extraordinary rate. These first stars are called population 3 stars, a classification distinct from the population 1 stars, young metal-rich stars like our sun, and population 2 stars, older, lower metallicity stars found in globular clusters and the galactic halo. Population 3 stars have never been directly observed. They burned bright and died fast in supernova explosions so energetic they could briefly outshine entire galaxies, seeding the universe with the first heavy elements. We have found indirect evidence for them in the chemical compositions of very old population 2 stars, which carry the fingerprints of whatever enriched the gas from which they formed. But no individual population 3 star has yet been detected. They were too far away, too faint, too ancient. Until Webb has not yet definitively confirmed a population 3 star, but it has detected spectral signatures consistent with extremely low metallicity galaxies in the early universe, galaxies whose light shows almost no evidence of elements heavier than helium, suggesting they are dominated by stars of the very first generation. This is one of the most active frontiers of current research with Webb's spectrographs. The first stars also emitted torrents of ultraviolet radiation. That radiation ionized the hydrogen in the universe around them, stripping electrons back off the neutral atoms that had formed 380,000 years after the Big Bang. This process, the epoch of ionization, transformed the universe's hydrogen from neutral back to ionized, and it marked the transition from the cosmic dark ages to the modern universe of galaxies and stars and light. This is the era that the James Webb Space Telescope was designed to observe. The cosmic dawn, the epoch of reionization, the first galaxies, the oldest light. But here is what makes the story so extraordinary. When Webb looked into that era, when it trained its gold mirrors on the most distant, most ancient patches of sky, what it found was not what the models predicted. Not even close. Chapter 3. The instrument that changed everything. before we get to the discoveries, we need to understand the instrument. Because the James Webb Space Telescope is not just a bigger Hubble. It is a fundamentally different kind of machine, built on different principles, operating in a different part of the universe, designed around a specific scientific question that Hubble could not answer. And understanding how it works is the only way to truly appreciate what it can see. The first thing to understand is the mirror. Hubble's primary mirror is 2.4 meters across, about the size of a large dining room table. It was famously launched with a subtle flaw in its curvature and had to be repaired by spacewalking astronauts in 1993. But even perfectly polished, 2.4 meters limits how much light you can collect. In optics, the larger the mirror, the more light it gathers, and the finer the detail it can resolve. Hubble's images are crisp and beautiful, but they are the product of a mirror the size of a dining table. Webb's primary mirror is 6.5 meters across, nearly 3 times the diameter of Hubble's, which means roughly 7 times the light collecting area. More light means you can detect fainter objects. Fainter objects means more distant objects. More distant objects means older light. But a 6.5 meter mirror cannot be launched in one piece. No rocket fairing is wide enough. So Webb's mirror is made of 18 hexagonal segments, each about 1.3 meters across, coated with a microscopically thin layer of gold. Gold, not aluminium as on Hubble, because gold is an exceptionally good reflector of infrared light, the kind of light Webb is designed to detect. The 18 segments were folded for launch, tucked inside the rocket's nose cone, and then unfolded and aligned with extraordinary precision after launch. Each segment adjusted by actuators to align them to within a fraction of the wavelength of light. The alignment process alone took weeks. The second thing to understand is the wavelength range. Webb operates primarily in the infrared, not the near-infrared that Hubble could partially access, but deep infrared, from about 0.6 micrometers just into the red end of visible light, all the way to 28 micrometers. This is the wavelength range in which the oldest galaxies in the universe, redshifted by cosmic expansion from ultraviolet to infrared, appear brightest. Webb was literally designed to see these specific wavelengths. It didn't just have broader capability than Hubble, it was optimized from the ground up to detect the specific light signatures of the first galaxies. But infrared astronomy has a problem. Infrared light is heat radiation. Everything warm emits infrared. The Earth emits infrared. The Moon emits infrared. The telescope itself, any room temperature telescope, glows in infrared, completely drowning out the faint signals from the distant universe. To solve this, Webb has to be cold, very cold. The science instruments on Webb must operate at temperatures below 50 Kelvin, about minus 223 degrees Celsius. The most sensitive detector, the mid-infrared instrument, or MIRI, must be cooled to about 7 Kelvin, 7 degrees above absolute zero. This is colder than most of deep space. To keep the telescope cold, Webb carries a sun shield, a 5-layer kite-shaped structure the size of a tennis court, made of a material called captain, coated with reflective aluminium and silicon. Each layer is thinner than a human hair. Together, they reduce the heat from the sun, Earth, and Moon by a factor of about 1 million. On the sun-facing side of the sun shield, temperatures reach about 85 degrees Celsius. On the telescope side, temperatures drop to minus 233 degrees. The sun shield is the thermal magic that makes the whole observatory possible. Webb orbits not around the Earth, like Hubble, but around the second Lagrange point, the L2 point, 1.5 million kilometers from Earth, on the far side from the Sun. At L2, the gravitational pulls of the Earth and Sun combine with the orbital mechanics to create a stable position where Webb can orbit the Sun while always keeping its sun shield between itself and the Sun, Earth, and Moon. The telescope is always cold. The sun shield always faces the warm direction. The orbit is stable for decades without major fuel expenditure. But getting to L2 was only possible because, for 30 years, a small army of engineers and scientists refused to give up on a telescope that repeatedly tried to kill itself in development. Webb was first formally proposed in 1989, just before Hubble launched, by a committee of astronomers thinking about what the next great space observatory should be. The early concept, then called the Next Generation Space Telescope, was for a large, cold, infrared telescope positioned at L2. The science case was clear: to see the first galaxies. To reach the redshifts Hubble could not. To detect the oldest light. What followed was one of the most grueling development sagas in the history of big science. The cost estimate, originally around $500 million, ballooned, first to $1 billion, then to $5 billion. Then, in a 2010 independent review that shook NASA management, it became clear the project was years behind schedule and billions over budget. Congress came close to canceling it entirely in 2011. The program survived, but with major restructuring, a new management team, and a hard commitment to a fixed budget ceiling of $8 billion. The final cost was roughly $10 billion. There were also purely technical near disasters. In 2018, during vibration testing at Northrop Grumman's facility in California, technicians discovered that the hundreds of tiny fasteners holding the sunshield covers in place had come loose, 178 of them in the first inspection. The fasteners had to be redesigned and replaced. In 2021, during launch, preparation at the Ariane 5 launch facility in French Guiana, a communication failure between the ground team and the spacecraft led to the clamp band release mechanism firing unexpectedly, sending a shock wave through the whole telescope. Engineers spent weeks checking for damage before clearing the telescope for launch. It launched on December 25, 2021. The deployment sequence over the following month was the most anxiety-inducing 2 weeks in NASA's recent history. 344 single points of failure, mechanisms that had to work perfectly in sequence, in space, with no possibility of servicing, including the complex folding and tensioning of the 5-layer sunshield, the unfolding of the secondary mirror, and the deployment of the 18-segment primary mirror. If any one of those 344 steps failed, the telescope was lost. None of them failed. On January 24, 2022, Webb fired its thrusters and settled into its halo orbit around L2. On July 12, 2022, the first science images were released. The world saw what 30 years of effort had built. The fourth thing to understand is the instrument suite. Webb carries 4 scientific instruments. NIRCam, the near-infrared camera, is the primary imager designed to capture the deep field images that have become Webb's most iconic outputs. NIR-SPEC, the near-infrared spectrograph, is perhaps the most scientifically powerful instrument, capable of taking spectra of up to 100 objects simultaneously, reading the chemical fingerprints and redshifts of 100 galaxies at the same time. NIRIS, the near-infrared imager and slitless spectrograph, provides additional imaging and spectroscopic capability. And MIRI, the mid-infrared instrument, operates at the longest wavelengths, seeing the most red-shifted light from the most distant sources. It is NIR-SPEC, particularly, that has been the engine of Webb's most important early discoveries. Because spectroscopy is not just about taking pretty pictures, it's about measurement. It's about reading the barcode of an object's light and extracting, with precision, its redshift, its chemical composition, its temperature, and its distance. A photograph tells you an object exists and roughly where it is. A spectrum tells you what it is, how far away it is, how old its light is, and what it's made of. Webb's ability to take simultaneous spectra of 100 objects at once, using a system of thousands of microscopic shutters, each individually controllable, called the micro-shutter assembly, has allowed it to characterize distant galaxies at a rate that previous instruments could never match. Hubble, taking one spectrum at a time, could spend days on a single galaxy. Webb can get 100 in the same exposure. The result is a machine purpose-built for the question, what did the universe look like at the beginning? And the answer it has returned is not what anyone expected. Chapter 4: The First Images and the First Shock. On July 12, 2022, NASA released the first full-resolution science images from the James Webb Space Telescope. The image that stopped the world was a deep field, a patch of sky about the size of a grain of sand held at arm's length, photographed for around 12 hours with Webb's NIRCam in multiple infrared wavelengths. The patch of sky, to the naked eye, looks essentially empty. No bright stars, no obvious objects, just darkness. In the image, thousands of galaxies. Not stars, galaxies. Each one a system of hundreds of billions of stars, each one a universe of its own scale and complexity, arrayed across the image like jewels on black velvet. Some are spirals, their structure visible even at these immense distances. Some are ellipticals, smooth and golden. Some are smeared into arcs, their shapes distorted by the gravity of foreground galaxy clusters, bending their light like a lens, a phenomenon called gravitational lensing, that both distorts and amplifies the images of distant objects. Some are tiny smudges of red, so small and faint they are at the edge of detection. The gravitational lensing deserves a moment of explanation because it's one of the ways Webb can see even further than its already extraordinary optics would allow. Einstein's general relativity predicts that mass curves spacetime, and light follows the curves of spacetime. A massive foreground object, a galaxy cluster containing hundreds of galaxies and enormous amounts of dark matter, curves the space-time around it enough that light from background objects traveling through that curved space-time is bent. Bent light from multiple paths around the cluster can converge on our telescope, meaning we detect light that would otherwise never have reached us. The cluster acts as a natural lens, magnifying the background objects by factors of 10 20, sometimes 100. The price is distortion. The lensed images appear as arcs, rings, or multiple copies of the same background object smeared around the lens. But the magnification is real. Some of the faintest objects Webb has detected, the most distant, most ancient galaxies in its deep fields, are detectable only because a fortuitously placed foreground cluster has magnified their light. Einstein's general relativity, formulated in 1915, before galaxies beyond the Milky Way were even confirmed to exist, is now a tool for building the universe's most powerful telescope. The universe itself is the instrument. Hubble, for all its achievements, had produced deep field images of comparable areas of sky over the course of decades of observation. The Hubble Ultra Deep Field, first released in 2004 and refined in subsequent observations, showed roughly 10,000 galaxies in a tiny patch of sky. It was one of the most significant astronomical images ever taken, a demonstration of the sheer density of the universe with light. Webb's first deep field image, taken in roughly 12 hours, reached galaxies Hubble had never seen. Objects at redshifts well above what Hubble's instruments could detect began emerging from the data. Tiny, faint, but spectroscopically measurable. The comparison was stark. What Hubble had achieved over years of patient accumulation, Webb began to surpass in its first full day of science operations. Those tiny red smudges, those were the ones that mattered. Because astronomers knew from the physics of redshift that the reddest objects in the image were the most distant. The red color was not intrinsic to the galaxies. It was the color of old light, stretched toward red by the expansion of the universe over billions of years. A galaxy at high redshift, a galaxy seen as it existed very early in the universe, would appear red because its original ultraviolet and visible light had been stretched into the infrared by the time it reached Webb's mirrors. And in that first deep field image, there were red objects that were redder than any objects ever previously detected. Objects that, if their redshifts were confirmed by spectroscopy, would represent the most distant, most ancient galaxies ever seen. The confirmation came in the following weeks and months. NIR-SPEC took spectra. Redshifts were measured, and the numbers that came back were extraordinary. In the first few months of science operations, Webb confirmed individual galaxy observations at redshifts above Z equals 10, then Z equals 11, then Z equals 12. At Z equals 12, we are seeing a galaxy as it existed when the universe was about 370 million years old, just 2.7% of its current age. The light from that galaxy has been traveling for over 13.4 billion years. When that light left, our Milky Way did not exist. The sun did not exist. The atoms in your body had not yet been forged. The universe was in its infancy, lit only by the very first generation of stars. And then came an object that broke the record in a way that made headlines around the world. JADES-GS-Z13-0. This galaxy, discovered in Webb's JADES survey, a deep imaging and spectroscopic program targeting two fields covering several hundred square arc-minutes of sky, was confirmed in late 2022 to have a redshift of Z equals 13.2. At that redshift, we are seeing it as it existed when the universe was approximately 320 million years old, less than 2.4% of the universe's current age. The light from JD's GSZ 13.0 that is currently hitting Webb's mirrors left that galaxy 13.46 billion years ago, when nothing that exists on Earth today had any history. No sun, no planet. The galaxy that would become our Milky Way was, at most, a diffuse cloud of gas slowly pulling together under gravity. And that galaxy, 320 million years after the Big Bang, already existed. It was already there, already luminous, already a galaxy rather than a gas cloud. This, by itself, was remarkable. But the real shock came not from how far away these galaxies were. It came from what they looked like, from how big they were, from how massive they were, from what they implied about the rate at which the early universe could form stars, at a rate that our models said was impossible. Chapter 5. Too Big, Too Soon, The Crisis in Cosmology. Here is a piece of physics that cosmologists believed until very recently, with considerable confidence. Galaxies form gradually. They form because dark matter, the invisible, gravitating substance that makes up about 27% of the universe, collapses under gravity into large halos, and ordinary matter, hydrogen and helium gas, falls into those dark matter halos and cools, eventually forming stars. The stars illuminate the galaxy. Over time, galaxies grow by forming more stars and by merging with other galaxies. The key word is gradually. In the standard cosmological model, the lambda CDM model, which describes a universe containing cold dark matter and a cosmological constant, structure in the universe grows hierarchically. Small. Things form first, then merge into bigger things. The first dark matter, hollows, were small. The first galaxies were small and faint. Over hundreds of millions to billions of years, they built up to the massive galaxies we see today. This model predicted that in the very early universe, the first few 100 million years, galaxies would be small, irregular, and of relatively low mass. The most massive galaxies we see in the nearby universe, giant ellipticals containing trillions of stars, assembled over billions of years of mergers, should not exist at high redshift. The universe simply hadn't had time to build them. This was not a speculative prediction. Lambda CDM is extraordinarily successful. It correctly predicts the large-scale structure of the universe, the cosmic web of filaments and voids that the galaxy surveys of the last 3 decades have mapped. It correctly predicts the abundances of the light elements from Big Bang nucleosynthesis. It correctly accounts for the temperature fluctuations in the CMB. It is the most tested cosmological model in history. And James Webb has found galaxies that may not fit it. In the first year of science operations, Webb's cameras and spectrographs began returning images and spectra of early galaxies that were, by the measurements, too massive. Not slightly too massive. Not at the edge of what models could accommodate, with some stretching of parameters. In some cases, the stellar masses implied by the data were an order of magnitude, or more above what the best simulations of early galaxy formation predicted should exist at those redshifts. The most dramatic result came from a study published in Nature in 2023, led by Ivo Labbé of the Swinburne University of Technology and his collaborators. They examined a sample of galaxies from Webb's first deep field imaging and identified 6 candidate objects at redshifts between about 7 and 10. corresponding to look-back times of 11 to 13 billion years. When they Rousseau estimated the stellar masses of these galaxies from their brightness and color, they found masses in the range of tens of billions to, in one case, potentially hundreds of billions of solar masses. For context, the Milky Way took about 13 billion years to accumulate its current stellar mass of roughly 60 billion solar masses. Some of these candidate objects appeared to have assembled comparable or greater stellar mass in the first billion years of the universe. The paper's language was measured, as scientific papers are, but the implications were immediately recognized. If these mass estimates were correct, and they came with significant uncertainties that the authors were careful to flag, then these galaxies existed in quantities and at masses that lambda CDM could not easily accommodate. Labbé and collaborators coined a memorable phrase for the problem. They called these objects universe breakers. The media ran with it. Headlines declared that Webb had broken cosmology, that our understanding of the universe was wrong, that the Big Bang Theory was in trouble. The hyperbole was, as it usually is, excessive, but the underlying scientific problem was real. Here was what made it specifically a problem, rather than just an interesting anomaly. In cosmology, you can always find individual objects that are unexpectedly large or unexpectedly early. The universe is vast and varied. Outliers happen. Statistical flukes produce occasional objects at the tail of the distribution. One unusual galaxy doesn't break a model, but Labbé's team wasn't reporting one unusual galaxy. They were reporting 6 candidate objects in a small patch of sky, and the implied number density of such massive early galaxies, the number per unit volume of space, was far higher than simulations predicted. It wasn't a fluke. It was a population of massive galaxies in the early universe, apparently too numerous and too massive to fit comfortably into lambda CDM. Not every team agreed with the mass estimates. Alternative analyses using different assumptions about the stellar populations in these galaxies produced lower mass estimates that were less alarming. Some researchers argued that the galaxies might be hosting AGN, active galactic nuclei, supermassive black holes actively accreting matter, whose bright emission was being mistakenly attributed to stellar mass. An AGN can outshine an entire galaxy. And if you think you're seeing stellar light, but you're actually seeing AGN emission, you will dramatically overestimate the stellar mass. This AGN question turned out to be more important than initially appreciated. Webb's subsequent spectroscopic follow-up of several of the most massive-looking early galaxy candidates revealed that a number of them do indeed host AGN. The active black holes in these objects were contributing significantly to the total luminosity, and removing the AGN contribution brought stellar mass estimates down to values less threatening to standard models. But it did not resolve the problem, because in the process of confirming AGN, Webb also confirmed something else: supermassive black holes in the early universe that are themselves too large, too soon. A black hole massive enough to power a luminous AGN at Z equals 10 or above must have grown to millions or billions of solar masses within the first few 100 million years of the universe. How? Black holes grow by accreting mass. Accretion takes time. Growing a supermassive black hole quickly requires either starting with an unusually massive seed, one larger than could be explained by the ordinary collapse of a single massive star, or accreting at rates above what standard physics allows, or both. Webb was not solving the too big too soon problem. It was revealing that the problem had multiple dimensions. Galaxies too massive, black holes too massive, star formation rates too high, all pointing the same direction. The early universe was assembling large structures faster than the models predicted. The debates were vigorous and public and ongoing, as good science should be. But even in the most conservative interpretations, something interesting and unexpected was going on in the early universe. The galaxies were forming stars faster than the models predicted. Not impossibly fast. Not universe-breakingly fast in most scenarios, but consistently, stubbornly, persistently faster. The star formation rates in early galaxies, the number of new stars being created per year, were, by the measurements, higher than simulations suggested they should be. Much higher in some cases. This could mean several things. It could mean the initial mass function, the distribution of stellar masses in newly formed star clusters, was different in the early universe, skewed toward more massive stars that are brighter and thus make the galaxy look heavier than it is. It could mean the efficiency with which gas in dark matter halos converts to stars was higher in the early universe than models assumed. It could mean there was a period of starburst activity, an intense, brief episode of extremely rapid star formation, early in the universe's history, that lambda CDM doesn't naturally produce. Or it could mean that the dark matter itself behaves differently on small scales than the simplest lambda CDM models assume. That the actual distribution of dark matter halos in the early universe was different from the predictions, allowing structure to form earlier and more efficiently than expected. All of these possibilities are being explored. None of them requires abandoning lambda CDM entirely. Most of them involve refinements to the physics of galaxy formation within lambda CDM, the baryonic physics of how gas cools, how stars form, how feedback from supernovae and black holes regulates star formation. These processes are notoriously difficult to simulate accurately, and it has long been known that the simplest models of early galaxy formation in lambda CDM underpredict star formation at high redshift compared to observations. But Webb has made the discrepancy larger and harder to ignore. It has pushed the problem from interesting tension at the edge of the data to systematic discrepancy that requires explanation. The scientific community is not panicking, but it is busy. Webb has generated a crisis, not a crisis of confidence in the Big Bang, but a crisis of productive uncertainty in our models of what happened in the first few 100 million years after it. And in the middle of that productive uncertainty, something else was happening. Something quieter, but potentially even more profound. Webb was finding galaxies at redshifts nobody had expected to reach. Not Z equals 13. Not Z equals 14. Higher. Objects that, if confirmed by spectroscopy, would push the boundary of the observable universe's earliest chapters further back than any previous instrument had managed. And in doing so, reveal something fundamental about the onset of the first light. Chapter 6. The Record Breakers. Pushing the Frontier. Further. Let's talk about what further actually means when you're talking about the edge of the observable universe. In the summer of 2023, A little over a year into Webb's science operations, a team of astronomers announced something that stopped the community cold. They had been working through data from the JADES survey, the same program that had produced JADES GSZ 13.0, the galaxy at redshift Z equals 13.2. They had been pushing for higher redshifts, looking for objects that were even fainter, even smaller, even more distant, objects whose light had been traveling even longer, objects that existed even closer to the very beginning of the universe. They found two: JADES GSZ 14.0 and JADES GSZ 14.1. The confirmations came in the spring of 2024 when NIR spectroscopy nailed down the redshifts precisely. JADES-GS-C 14-0 has a confirmed spectroscopic redshift of Z equals 14.32. JADES GSZ 14.1 sits at Z2 equals 13.9. These are not photometric estimates based on the colors of an object in an image, which carry significant uncertainty. These are spectroscopic confirmations, where Webb has read the precise barcode of the galaxy's light and measured the exact stretching of its spectral lines. The numbers are not approximate, they are measured. At Z equals 14.32, we are seeing JADES GSZ 14.0 as it existed when the universe was approximately 290 million years old, less than 2.1% of the universe's current age. The light from this galaxy has been traveling for 13.5 billion years. But here is what stunned the researchers who measured it. JADES GSZ 14.0 is not a tiny, faint, barely there smudge. It is, for its epoch, surprisingly large and surprisingly bright. Its physical diameter spans roughly 1,600 light-years, already the size of a significant dwarf galaxy today, and far larger than simulations predicted early galaxies at this epoch should be. More strikingly, it appears to be actively forming stars at a rate of roughly 20 solar masses per year. 20 times the mass of our sun's worth of new stars being created every 12 months. And the spectrum shows something that absolutely should not be there at that redshift. Oxygen. Oxygen is a heavy element. It does not exist in primordial gas. It is produced in the cores of massive stars, specifically in the triple alpha process, where helium nuclei fuse into carbon and then oxygen, and it is released into the interstellar medium when those stars explode as supernovae. The presence of detectable oxygen in JADES NSZ 14.0 means that at least one full generation of massive stars has already lived, burned, and died in this galaxy before we are observing it. All of this happening within the first 290 million years of the universe's existence. The universe, at 290 million years old, had already cycled through a generation of stars in this galaxy. Massive stars that formed from primordial gas, burned through their fuel in a few million years, exploded in supernovae that scattered oxygen and other heavy elements into the interstellar gas, and then a next generation of stars had already formed from that enriched material by the time the light we're detecting was emitted. Let's really sit with the timeline here. The universe is 13.8 billion years old. We are seeing this galaxy 290 million years in, about 2% of the way through cosmic history. In that 2%, an entire stellar generation has been born, lived, and died. The stars that created the oxygen we're detecting in JD's GSZ 14-0 probably lived for only a few million years. Massive stars burn bright and die young, so somewhere between 200 and 285 million years after the Big Bang, the first stars in this galaxy formed, spent a few million years burning at temperatures of tens of thousands of Kelvin, then exploded, and a second generation formed from their remains. Our sun has been burning for 4.6 billion years. It will burn for another 5 billion years. It is, by stellar standards, an extraordinarily unhurried object. The first stars that created the oxygen in JD's GSZ 14-0 lived and died in less time than it takes our solar system to complete one orbit around the galactic center. This oxygen detection has an additional implication that the research team was careful to highlight. It means JADESGSZ 14-0 is not a primordial galaxy. It is not a first-generation object. It is already chemically evolved, already enriched with heavy elements, already past its first chapter. The true first galaxies, the ones that formed from completely primordial hydrogen and helium, the ones that hosted the very first population 3 stars, must have existed even earlier. We are not yet seeing the beginning. We are seeing the second chapter. The first chapter is still out there, still waiting, at redshifts higher than Z equals 14, in light that is currently at the very edge of Webb's sensitivity, or perhaps beyond it. The record that JD's GSZ 14-0 represents is not the oldest possible light. It is the oldest light we have confirmed so far. Those two things are very different, and understanding the gap between them is what drives the field forward. The timeline is brutally compressed. Our sun has been burning for 4.6 billion years and has barely reached middle age. These first-generation massive stars lived and died in a few million years, a timescale that is to the current universe what a single day is to a human lifetime. But even the presence of oxygen in a 290 million-year-old galaxy, extraordinary as it is, was not the most surprising thing in the data coming out of Webb's first few years of operation. Because a different team, working on a different target with a different instrument configuration, was about to find something that pushed the frontier even further, and raised a question that cosmologists are still arguing about. In early 2024, another galaxy candidate emerged from deep spectroscopic data. Designated JD's GSZ 16-1, it showed tentative evidence for a redshift approaching Z equals 16. At that redshift, we would be seeing a galaxy as it existed when the universe was approximately 230 million years old. Not yet confirmed with the same confidence as JD's GSZ 14-0, but being actively pursued. And even if Z equals 16 falls, even if the spectroscopy comes back with a lower number, the trajectory is clear. Every year, Webb is pushing the confirmed redshift frontier further. Every year, the oldest confirmed light gets older. The record that stood before Webb, held by a galaxy called GN-Z11, confirmed at Z equals 10.9 by Hubble and ground-based telescopes, has been comprehensively broken multiple times over in the space of 2 years. The question is no longer whether Webb can reach cosmic dawn. It is how close to the very first stars it can get, and what it will find when it gets there. To appreciate what those numbers represent, It helps to understand what the frontier looked like before Webb arrived. GN-Z11 was, for years, the most distant galaxy ever spectroscopically confirmed. It was discovered in Hubble imaging of the Candles survey and confirmed in 2016 by a team using the Keck Observatory in Hawaii. The redshift is Z equals 10.96, placing it at a time when the universe was approximately 430 million years old. The confirmation made international news. At the time, it was genuinely unprecedented. Hubble had pushed as far as it could go, and the Keck telescope had stretched its spectroscopic reach to the absolute limit of what ground-based infrared astronomy could manage. GN-Z11 sat there as a record for 6 years, essentially untouchable. Then Webb launched. In its very first year of science operations, before its first anniversary, Webb had confirmed multiple galaxies beyond Z equals 10. Within 18 months, it had surpassed Hubble's best by more than 3 redshift units and hundreds of millions of years of look-back time. The record GN-Z11 had held for 6 years was broken, then broken again, then broken a third time. What had been the absolute frontier of human observational reach became, within 2 years of Webb's first light, a relatively nearby and well-characterized object that Webb can now study with relative ease. GN-Z11 itself has become a scientific target of renewed interest under Webb's scrutiny. Where Hubble could only confirm its redshift and estimate its brightness, Webb has now taken detailed spectra of GN-Z11, revealing that it hosts an AGN, an active black hole in its center, contributing significantly to its luminosity, and has measured the properties of its interstellar gas, its ionization state, and its chemical abundance pattern in detail that was simply impossible with Hubble. An object that was once at the very frontier of detection is now a well-studied specimen. This is what progress in observational astronomy looks like. Yesterday's record breaker becomes tomorrow's reference object. The instrument that could barely detect GN-Z11 at all is succeeded by an instrument that can characterize it in detail and find objects 3 times further away in the same breath. The frontier moves, and as it moves, it doesn't just reveal new objects. It deepens our understanding of everything it passes on the way. JADES-GS-Z14-0 is where the frontier sits today. In 5 years, it may be a reference object too, something Webb's successors use for calibration, while their primary science targets sit at Z equals 16, Z2 equals 18, at the very edge of what existed before the first stars had time to enrich anything. And even if Z equals 16 falls, even if the spectroscopy comes back with a lower number, the trajectory is clear. Every year, Webb is pushing the confirmed redshift frontier further. Every year, the oldest confirmed light gets older. Chapter 7: The Epoch of Rionization. The universe's second great transformation. To understand why finding these galaxies matters beyond just setting distance records, you need to understand the epoch of reionization, one of the most important and least discussed transformations in the history of the universe. We talked about the first transformation in Chapter 2. At 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons into neutral hydrogen atoms. The fog cleared, the CMB was released. This was recombination, the first great phase change of the universe, from opaque plasma to transparent gas. The second great transformation was reionization, and understanding it requires understanding the state the universe was in before it happened. After recombination, the universe was filled with neutral hydrogen gas. Neutral hydrogen is extraordinarily effective at absorbing ultraviolet photons, specifically photons with enough energy to ionize it, to knock the electron back off the atom. This absorption creates what astronomers call the Lyman break, a sharp cutoff in the spectrum of any source seen through a significant column of neutral hydrogen, where all the ultraviolet photons have been absorbed. In the early universe, before the first stars switched on, the neutral hydrogen fog filled all of space. If you could have placed yourself in that fog and looked in any direction, you would have seen nothing. Not the darkness of space as we know it, a genuinely opaque fog of neutral gas, darker than any darkness, impenetrable to any electromagnetic radiation above a certain energy. When the first stars formed and began emitting ultraviolet radiation, they started ionizing the hydrogen around them. Each star carved out a growing bubble of ionized, transparent gas around itself. At first, these bubbles were isolated, islands of transparency in a sea of neutral fog. The universe was patchy, some regions clear, most still opaque. Over hundreds of millions of years, as more and more galaxies formed and more ultraviolet radiation was produced, the bubbles grew and merged. The sea of neutral hydrogen gradually dissolved, eaten away by the relentless ultraviolet output of billions of young hot stars in thousands of early galaxies. Eventually, somewhere around Z equals 6, roughly a billion years after the Big Bang, the last neutral hydrogen in the intergalactic medium was ionized. The universe became transparent, everywhere, to ultraviolet radiation. Reionization was complete. This is a profound event. The universe went from opaque fog to transparent clarity permanently, and it was powered by the collective ultraviolet output of the first galaxies. The very galaxies Webb is now detecting at Z equals 10, 12, 14. These are the sources that drove reionization. They are the engines that cleared the fog. Understanding reionization is not just an academic exercise in cosmic history. It is crucial for understanding how the universe became the way it is today, how it came to have the intergalactic medium we observe, the temperature structure of the cosmic web, the properties of the gas between galaxies that we detect in the spectra of distant quasars. And Webb is, for the first time, giving us the observational data to test our theoretical models of reionization from the source side, the galaxy side. We can now, with Webb, directly detect and characterize the galaxies that were responsible for reionization, measure their ultraviolet luminosities, measure their escape fractions, the fraction of ionizing photons that actually made it out of the galaxy into the intergalactic medium, and ask whether the total ionizing photon budget from early galaxies was sufficient to drive reionization on the observed timeline. The early results from Webb are fascinating and slightly troubling. The escape fraction, the fraction of ionizing photons that escape galaxies into the intergalactic medium, turns out to be highly variable and, in some cases, surprisingly high. Some early galaxies appear to be leaking significant amounts of ultraviolet radiation, which is exactly what you need to ionize the surrounding intergalactic medium. Others appear much more opaque. More of their radiation is absorbed internally before it can escape? What determines the escape fraction? This is one of the open questions that Webb is now in a position to begin answering. The geometry of the star-forming regions within the galaxy, the distribution of dust and gas, the presence of pathways carved by supernova explosions, all of these appear to play a role. Webb is beginning to resolve the internal structure of some of these early galaxies well enough to start connecting their physical properties to their ionizing photon output. The picture of reionization that is emerging from Webb's data is more complex and more varied than the simple models assumed. It was not a smooth, uniform process. It was patchy and irregular and driven by heterogeneous population of sources, some galaxies contributing enormously, others barely contributing at all. The universe cleared its fog galaxy by galaxy, bubble by bubble, over hundreds of millions of years, in a process whose details we are only now beginning to observe directly. One of the key diagnostic tools astronomers use to probe reionization comes not from imaging early galaxies directly, but from studying what the neutral hydrogen fog does to background light. When you observe a distant quasar, a blazingly luminous object powered by a supermassive black hole, bright enough to be seen across the entire observable universe, its light passes through vast columns of intergalactic hydrogen on its way to your telescope. Neutral hydrogen absorbs that light at very specific wavelengths with extraordinary efficiency. If the gas between the quasar and US is predominantly neutral, the spectrum of the quasar shows a complete absorption trough. Astronomers call it the Gunn-Peterson trough, where essentially all the light at certain wavelengths has been swallowed by the intervening fog. If the hydrogen is fully ionized, as it is in the nearby universe today, those wavelengths pass through relatively cleanly. By studying the spectra of quasars at different redshifts, astronomers can measure how opaque the intergalactic medium was at each epoch in cosmic history. The data is clear. Above redshift Z equals 6, the neutral hydrogen fraction climbs sharply. At Z equals 7, a significant fraction of the intergalactic medium was still neutral. At Z equals 7.5 and above, the fog was thick enough to completely suppress the quasar light at the relevant wavelengths. This technique gives us the timeline. Reionization was largely complete by Z equals 6 and still significantly underway at Z equals 7 to 8. But it does not tell us who drove it, which galaxies produced the ionizing photons that burned through the fog. Were there rare, extremely luminous sources that dominated the budget, or was it the collective drizzle of ultraviolet light from billions of faint, ordinary galaxies? Before Webb, answering this was nearly impossible. The galaxies at Z equals 6 to 10, the prime suspects, were either too faint to characterize spectroscopically or required hundreds of hours on the world's largest ground-based telescopes to yield even a single usable spectrum. Progress was glacially slow. Webb has completely changed the economics of this investigation. With NIR SPEC's micro-shutter assembly taking spectra of up to 100 objects simultaneously, Webb can characterize the reionization-era galaxy population at a rate that was unimaginable before. In the first 2 years of operations, it has compiled spectroscopic samples of hundreds of galaxies at Z equals 6 to 10, more in 2 years than previous instruments had managed in 2 decades. The emerging conclusion is striking. Faint, low-mass galaxies appear to dominate the ionizing photon budget, not rare luminous quasars as some models predicted, but the collective output of an enormous population of small, intensely star-forming systems, each individually insignificant but collectively powerful enough to ionize the universe. The fog did not clear because of a few blazing searchlights. It cleared because billions of candles lit all at once. And through that fog, barely at the edge of detection, at redshifts where even Webb struggles to gather enough signal, we are beginning to glimpse the earliest individual objects, not just the statistical properties of early galaxy populations, but specific, named, spectroscopically confirmed galaxies from when the universe was barely 2% of its current age. Each one of those galaxies is a message from the beginning, and reading the messages is changing what we thought we knew. Chapter 8. What this actually means for the Big Bang. Let's be precise here, because this is where the science communication around Webb has, in some places, gone badly wrong, and where the genuine scientific significance of what Webb has found deserves a more careful treatment than the headlines have given it. You have probably seen articles with headlines like, "James Webb breaks cosmology," or "Webb finds galaxies that shouldn't exist." Or more dramatically, has Webb disproved the Big Bang? No, it has not disproved the Big Bang. The Big Bang is one of the most comprehensively verified theories in all of science. It is supported by multiple independent lines of evidence, each of which is so strong that no alternative model has ever come close to accounting for all of them simultaneously. Let me give you the 3 pillars because they are worth knowing. First, the expansion of the universe. In 1929, Edwin Hubble published observations showing that virtually all distant galaxies are moving away from us, and that the further away they are, the faster they are receding. This is exactly what you expect in a universe that was once compressed into a small volume and has been expanding ever since. The Big Bang predicts the expansion. The expansion is observed. This observation is so robustly confirmed by so many independent methods over nearly a century that it is not seriously contested by any credible cosmologist anywhere in the world. Second, Big Bang nucleosynthesis. The Big Bang predicts that in the first few minutes, when the universe was hot enough for nuclear fusion, specific amounts of hydrogen, helium, and lithium should have been produced. The prediction is precise. The ratio of hydrogen to helium should be about 75 to 25% by mass, with trace amounts of lithium. When astronomers measured the helium and lithium abundances in the oldest, least processed stars and gas clouds, objects whose chemical composition reflects primordial abundances before stellar nucleosynthesis had much chance to alter them. The measured ratios match the Big Bang nucleosynthesis predictions to remarkable precision. This is not a tunable result. The physics of nuclear reactions in the first 3 minutes is well understood. The prediction is specific. The observation matches it. Third, the cosmic microwave background. The Big Bang predicts that the universe, before it cleared at 380,000 years, was a hot plasma in thermal equilibrium. When it cleared, the radiation it released should have a specific thermal spectrum, a perfect black body. At a specific temperature, now cooled by expansion to about 2.7 Kelvin. the CMB has been measured with extraordinary precision by COBE, WMAP, and Planck. It is a perfect black body to within 1 part in 10,000. Its temperature is 2.725 Kelvin. The tiny fluctuations in its temperature across the sky match the predictions of inflation-seeded density perturbations in a Big Bang universe. These 3 pillars are not threatened by Webb's discoveries, not even slightly. What Webb has found is not evidence against the Big Bang. It is evidence that our model of what happened after the Big Bang, specifically our model of how quickly galaxies assembled in the first few 100 million years, needs revision. This is a completely different kind of problem, and it is the normal, healthy operation of science. The standard model of cosmology, lambda CDM, is extraordinarily successful at describing the universe on large scales. It correctly predicts the large-scale structure. It correctly predicts the CMB. It correctly predicts the abundance of light elements. But it contains submodels, models of galaxy formation, star formation, black hole growth, and feedback processes that are far less certain. These are the areas where Webb's data is creating tension, not with the Big Bang, with our models of galaxy formation within a universe that began with the Big Bang. The distinction matters enormously. Revising a model of galaxy formation within lambda CDM is a normal, expected, scientifically productive thing to do. Finding that the subgrid physics in our simulations was wrong, that we underestimated star formation efficiency or overestimated the effect of supernova feedback in early galaxies, or got the initial mass function wrong, is a discovery, not a crisis. Let's be concrete about what this revision actually looks like, because revising galaxy formation models can sound vague in a way that obscures how specific and how scientifically meaningful it actually is. Modern simulations of galaxy formation in a lambda CDM universe, programs like Illustri's TNG, Eagle, Fire, and their successors, model the formation of galaxies by tracking dark matter, gas, stars, and black holes across billions of years of cosmic evolution. They handle gravity exactly. They model gas dynamics and cooling, but they cannot resolve the physics of individual star formation events, or the detailed dynamics of supernova explosions, or the precise way that radiation from hot, young stars heats and disperses the surrounding gas. These processes happen on scales of light years, but the simulation boxes cover billions of light years and have numerical resolution of thousands of light years at best. The small-scale physics has to be approximated, put in by hand as recipes, parameterized, calibrated against observations. These recipes are called subgrid physics, and the tension Webb has revealed is pointing specifically at several of them. The first is the stellar feedback recipe. In modern simulations, when a region of gas forms stars, the massive stars among them live briefly and then explode as supernovae. Those explosions deposit energy into the surrounding gas, heating it, driving outflows, suppressing further star formation. This is stellar feedback, and it is one of the most important regulators of galaxy growth. Without it, simulations produce galaxies that are too massive, forming stars too fast, bearing no resemblance to observed galaxies. The strength of this feedback, how much energy from each supernova couples to the surrounding gas, how efficiently it drives outflows, is a parameter that is tuned to match observations of nearby galaxies. But those nearby galaxies formed in the last few billion years in conditions very different from the first 500 million years. The gas density was higher then. The metallicity was lower, which means the cooling physics was different. The interstellar medium was more turbulent. The dark matter halos were smaller. The conditions were unlike anything we can observe locally. There is no guarantee that feedback recipes calibrated on modern galaxies work correctly in the early universe. Webb's discoveries suggest they don't. That feedback in the early universe was less efficient, or differently distributed, or operating on a different timescale than the recipes assume. The second is the initial mass function. When a gas cloud forms a cluster of stars, the distribution of stellar masses, how many massive stars versus how many small stars form per unit mass of gas, follows a statistical distribution called the initial mass function. In nearby star-forming regions, this distribution is well measured. It follows a specific power law form with far more small stars than massive ones. It is usually assumed to be universal, the same in the early universe as in the local universe today. But there are theoretical reasons to expect it wasn't. In the early universe, the gas was warmer on average. The CMB temperature was higher at high redshift, providing a thermal floor that prevented gas from cooling as far as it can today. Warmer gas forms larger fragments. Larger fragments produce more massive stars. A top-heavy initial mass function in the early universe, more massive stars per unit gas mass, would produce more ultraviolet radiation per unit stellar mass formed, making early galaxies look brighter and more massive than a standard IMF would predict. It would also produce more supernovae per unit gas mass, more heavy element enrichment per unit star formation, and faster chemical evolution. All of these are consistent with what Webb is observing. The third is the dust model. Dust in galaxies absorbs ultraviolet and optical starlight and re-emits it in the infrared. How much dust a galaxy contains and where that dust is distributed determines how much of its light we see at different wavelengths. Early galaxies, forming from nearly pristine gas with few heavy elements, might be expected to have very little dust. And some early galaxies Webb has observed do appear remarkably dust poor. But others show evidence for significant dust content, even at very high redshift. The dust formation and destruction physics in these early systems is poorly understood, and getting it wrong leads to incorrect estimates of star formation rates and stellar masses. All three of these, feedback efficiency, the initial mass function, and dust, are areas where the simulations need to be tested against Webb's data and, where they fail, revised. This is ongoing. It is producing papers at a rate that the community is still absorbing. It is the scientific process working exactly as it should. Observation confronting theory, theory updating, new predictions being made and tested. What some researchers have proposed is more radical. A small number of cosmologists, genuinely small, not a growing mainstream, have suggested that Webb's results might require modifications to lambda CDM at a more fundamental level. Not just revised galaxy formation physics, but perhaps a different dark matter model, or a different treatment of early universe physics, or even a different cosmological framework entirely. The most frequently mentioned alternative is a class of models called early dark energy. Proposals in which an additional energy component, similar to dark energy but operating at early cosmic times rather than late, temporarily accelerated the expansion of the universe in the first million years. Early dark energy would have changed the growth rate of cosmic structure in the early universe, potentially allowing larger structures to form earlier. It would also address another tension in lambda CDM, the Hubble tension, the discrepancy between different measurements of the current expansion rate of the universe. The Hubble tension deserves a moment of its own because it is the most significant crack in lambda CDM that currently exists. Independent of anything Webb has found, and predating Webb entirely. The Hubble constant, the rate at which the universe is currently expanding, measured in kilometers per second per megaparsec, can be measured two completely independent ways. The first way uses the early universe. You take the precise CMB data, fit a lambda CDM model to it, and predict what the Hubble constant should be today, based on how the universe has evolved from that early state. The Planck satellite's CMB data gives a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The second way uses the late universe directly. You build what astronomers call the distance ladder, using Cepheid variable stars to calibrate distances to nearby galaxies, then using type 1a supernovae in those galaxies as standard candles to measure distances further out, building up to a direct measurement of how fast galaxies at known distances are receding. Multiple teams using this method consistently get a Hubble constant of approximately 73 kilometers per second per megaparsec. These two numbers disagree by about 8%. That sounds small. It isn't. Given the precision of the measurements on both sides, the CMB measurement is precise to about 0.5%, the distance ladder measurements to about 2%. This discrepancy is statistically significant at more than 5 sigma. In particle physics, 5 sigma is the threshold for claiming a discovery. The Hubble tension is, in the statistical sense, a confirmed discrepancy between two well-measured quantities that the standard model says should agree. Either one of the measurements is wrong, which many teams have checked multiple times with multiple methods, and the discrepancy persists, or lambda CDM is missing something that changes the expansion history between the early and late universe, enough to shift the predicted Hubble constant by 8%. Early dark energy is one proposal. Modified gravity is another. An unknown early universe radiation component is a third. None of them has been confirmed. None of them perfectly fits all the available data. The Hubble tension remains open, the most significant observational anomaly in cosmology today, older than Webb, and deeper than anything Webb has found. Webb is contributing to this story indirectly by providing better constraints on galaxy distances at intermediate redshifts, and by testing the calibration of the distance ladder at higher redshifts than Hubble could reach. Webb is helping to check whether the distance ladder measurements have systematic errors that could explain the tension. So far, the tension persists. These are real and active areas of research. They are not crackpot alternatives. They are papers published in peer-reviewed journals by credentialed cosmologists working within the mainstream of the field. But they are also not yet evidence-based modifications. They are theoretical proposals motivated partly by the drive to find a solution and partly by data that is in the most candid assessment, still at the stage of tension rather than decisive contradiction. The honest summary of what Webb has found for Big Bang cosmology is this. It has identified systematic discrepancies in our models of early galaxy formation that require explanation and are driving significant theoretical effort. It has not found anything inconsistent with the Big Bang itself. It has not found anything that requires discarding or fundamentally replacing lambda CDM. But it has found enough that is unexpected at enough redshifts in enough independent surveys that the galaxy formation community is now genuinely uncertain about which direction the solution lies, and that uncertainty is enormously productive. The universe, as Webb is showing us, is more surprising than we thought. It always is. Chapter 9, What Comes Next? The Future of Seeing Old Light. Webb is right now still operating, still taking data, still breaking records, still generating papers at a rate that has overwhelmed the ability of the field to fully absorb and interpret what it's finding. And it is only at the beginning. Webb was designed for a mission lifetime of 10 years, with consumables, primarily the fuel for station keeping, sized for 20. The launch was so precise, the trajectory so accurate, that Webb used far less fuel than budgeted during its journey to L2. Current estimates suggest the telescope has fuel for at least 20 years of operations, possibly significantly more. 20 years of James Webb Space Telescope data. It's worth pausing on what that means in practice. In astronomy, the development of a major observatory produces a kind of scientific compound interest. The first year produces discoveries. The second year produces follow-up observations of those discoveries, deepening understanding. The third year, researchers who built their research programs around the new capabilities start returning results from long, carefully planned programs. By year 5, the data archive is large enough that researchers are finding things in archival data that nobody specifically looked for. By year 10, the observatory has transformed not just one field, but multiple fields, in ways that couldn't be predicted at launch. Hubble was launched in 1990. It is still operating, still producing science 35 years later. The Hubble Ultra Deep Field, the deep stare into a patch of sky that revealed 10,000 galaxies, wasn't taken until 2003, 13 years into Hubble's mission. Some of Hubble's most significant science has come in the last decade, long after the observatory was expected to have run its course. Observatories, when they work, keep giving. Webb will do the same. In the years ahead, there are specific scientific programs whose results will almost certainly redefine what we know about the early universe. The first is the characterization of population 3 star candidates. Webb has already found galaxies at Z equals 14 with spectra that show almost no metal content. Galaxies whose gas is nearly pristine, with chemical abundances barely above primordial. Some of these objects may contain significant fractions of population 3 stars, the first stellar generation that has never been directly confirmed. As Webb accumulates deeper data on these objects, and as gravitational lensing provides occasional chance magnifications of extremely faint early sources, the probability of a confirmed population 3 detection grows. A confirmed detection would be one of the great milestones of 21st century astronomy, the first direct observation of the universe's first stars. The second is the mapping of Ryanization topology. Right now, Webb is building statistical samples of reionization-era galaxies. In the years ahead, with enough galaxies characterized across enough sightlines, it will become possible to map the patchiness of reionization in 3 dimensions, to see where the ionized bubbles were large and where they were small, which regions cleared early and which cleared late, and how the topology of reionization connects to the underlying dark matter structure. This is something no instrument before Webb could even approach. The third is the deep characterization of the most extreme early objects. Several of the massive early galaxy candidates that generated the Universe Breakers discussion are now known to host AGN. The whole spectroscopic characterization of these systems, measuring the mass of the central black holes, the velocity dispersions of the surrounding stars, the gas phase metallicities of the interstellar medium, will tell us how the relationship between black holes and their host galaxies was established in the first billion years. In the nearby universe, there is a tight correlation between black hole mass and the properties of the host galaxy's bulge, a correlation that implies the black hole and the galaxy co-evolved. Did that co-evolution begin immediately, in the first billion years? Or was the early universe a time when black holes grew independently before the galaxy caught up? Webb is in the process of answering this. The fourth is the detection of the first quasars. Several luminous quasars are already known at Z equals 7 and above. Objects whose central black holes have masses of hundreds of millions to billions of solar masses, all assembled within the first billion years. The physics of how these objects formed is one of the deepest unsolved problems in high redshift astronomy. Webb's spectroscopic characterization of these quasars, measuring their black hole masses, their host galaxy properties, the chemistry of their surrounding gas, is ongoing and accelerating. On the ground, the next generation of extremely large telescopes is under construction. The European Southern Observatory's extremely large telescope in Chile, with a primary mirror 39 meters across, will complement Webb by providing extremely high-resolution spectroscopy of Webb-identified targets. Resolving the kinematics of individual star-forming regions within high redshift galaxies and measuring the detailed chemical abundances that tell us about their stellar populations, it will be able to do in minutes what would take Webb hours for the brightest high redshift targets. The Atacama Large Millimeter Array, ALMA, continues to operate alongside Webb, providing measurements of cold gas and dust in early galaxies that Webb's infrared instruments cannot access. The combination of Webb's rest frame ultraviolet and optical data with ALMA's sub-millimeter data is giving a 3-dimensional picture of early galaxy structure. Stars here, gas there, dust concentrated in those regions, molecular outflows carved by supernovae, that no single observatory could provide alone. And further ahead, the Nancy Grace Roman Space Telescope, already built, awaiting launch, will survey enormous areas of sky in the infrared, identifying the statistical samples of distant galaxies that Webb's limited field of view cannot efficiently assemble. Roman will find thousands of candidate high redshift galaxies. Webb will follow up on the most interesting ones with deep spectroscopy. The 2 telescopes are designed to work together, and their combined science program in the late 2020s will push the frontier of early universe astronomy further and faster than either could alone. The first stars, population 3, the objects whose ultraviolet radiation reionized the universe, whose supernova explosions seeded the first heavy elements, whose gravitational remnants may be the seeds of the supermassive black holes we observe everywhere in the modern universe. We have never detected one directly. We have indirect evidence for their existence in the chemistry of old stars, in the statistics of early galaxies, in the models of reionization that require their photons. But we have not seen one. That is arguably the great remaining observational frontier of early universe astronomy. To detect the light from a single population 3 star, or the first star cluster, or the first episode of star formation in the universe. To literally see the moment when the lights turned on after 200 million years of darkness. Webb may be able to do it, possibly in the next 5 years. Possibly in the next 10, the candidates are being identified. The gravitational lenses that could amplify them to detectability are being cataloged. The observation programs are being planned. If it happens, when it happens, it will be the deepest look into cosmic history that any instrument has ever achieved. It will be light that has been traveling since the universe was perhaps 100 to 200 million years old. Light from objects that no longer exist, that burned out billions of years before the Earth formed. Light older than anything we have ever detected. Conclusion: what the oldest light tells us. Let me take you back to the beginning, to that grain of sand held at arm's length, covering a patch of night sky so small you would never voluntarily look at it. To the 12 hours of staring, gold mirror accumulating photons one by one. To the image that emerged, thousands of galaxies in a space you thought was empty. And to the tiny red smudge at the edge of that image. Barely resolved, barely detectable, so faint that the photons, arriving per second, could be counted. That tiny red smudge is Jade's GSC 14-0, the most distant, most ancient confirmed galaxy in the observable universe as of this recording. A galaxy that existed 290 million years after the Big Bang. A galaxy already large enough, already star-forming rapidly enough, already chemically enriched enough, already oxygen-bearing, to challenge our best models of early cosmic structure. The light from that galaxy has been in flight for 13.5 billion years. When it left, the universe was a hot, dense, chaotic place of young stars and virgin gas, lit by ultraviolet radiation so intense it was slowly ionizing the hydrogen fog it had cleared just 250 million years before. The Milky Way did not exist. The Sun, which would not form for another 9 billion years, did not exist. The Earth would not exist for another 9.5 billion years after that. The atoms that form your body, the carbon, the oxygen, the calcium, the phosphorus, were not yet scattered across space. They were inside those first fierce, short-lived stars in the cores of objects just like JD's GSC 14-0, being forged in nuclear fires that burned for a few million years before going out in catastrophic explosions. Those explosions were not just endings, they were beginnings. Every supernova in the early universe was a seed event. The explosion dispersed the heavy elements forged inside the star, the carbon, oxygen, silicon, magnesium, iron, into the surrounding interstellar gas. That gas, now chemically enriched, cooled more efficiently than primordial gas, it fragmented more readily. It produced the next generation of stars, smaller, more numerous, longer lived. Each generation of stars enriched the gas further, making each subsequent generation still more chemically complex. Over billions of years, the gas in galaxies like ours accumulated enough carbon, oxygen, and silicon to eventually form rocky planets. Enough complex chemistry to eventually form organic molecules. Enough of the right conditions to eventually, in at least one place, cross the threshold from chemistry to biology. Every atom in your body was processed through at least one stellar interior, probably several. The iron in your blood was forged in a supernova. The calcium in your bones was forged in a massive star's core in the last moments before it collapsed. The oxygen you are breathing right now was made in the nuclear burning shells of stars that died billions of years ago and scattered their contents into the galaxy. The carbon that forms the backbone of every DNA molecule in every cell in your body was synthesized in the triple alpha process inside stars that no longer exist. You are, in the most literal physical sense, made of the universe. Not metaphorically, not poetically. The atoms in your body were, at some point, inside a star. The information about those atoms' history is carried in their isotope ratios, in the relative abundances of elements, in your body, in the chemical signature of the stellar populations that enriched the gas from which your solar system formed. And the first chapter of that history, the very first forging of the very first heavy elements in the very first stars, is what Webb is now reading. The light from Jade's GS 14-0 carries within its oxygen spectral line the signature of the generation before it, the stars that created the oxygen it contains. Those stars existed perhaps 50 to 100 million years before the galaxy we are observing. They exist at a redshift somewhere above Z equals 16, in light we have not yet detected, in a chapter we have not yet read. And then those stars died, and the elements spread, and more stars formed from the enriched gas, and galaxies grew and merged and built themselves over billions of years. And one of those galaxies, 12 billion years after JD's GSZ 14-0, assembled a spiral disk around a yellow star in a quiet arm, and one of the billions of planets around that star developed chemistry, and that chemistry developed biology. And that biology, after 4 billion years of iterative refinement, eventually produced something that could look back. Something that could build a gold mirror telescope and send it to a gravitational equilibrium 1.5 million kilometers away and focus it on a patch of darkness and wait and accumulate photons and measure their wavelengths and compute a redshift and say, this light left its source 13.5 billion years ago. This is the oldest light we have ever seen. That chain of events, from the first stars in Jade's GSZ 14-0 to the photon landing on Webb's mirror, is the deepest thread connecting the beginning of the universe to the present moment. Every atom in every instrument we used to detect that light was forged in a star. The physics that governs the gold mirror's reflectivity was worked out by scientists whose atoms were forged in stars. The mathematics that lets us compute the redshift and the look back, time was discovered by minds made of atoms forged in stars. We are made of the universe, and we have turned around and looked at it from the inside, all the way back to near its very beginning. But here's the thing I want to leave you with. This is not the end of the story. It is the most exciting possible point in the middle of it. The oldest light we've detected keeps getting older. When Hubble was at its best, the oldest confirmed galaxy was at Z equals 10. Webb has already pushed that to Z equals 14.3. The frontier is moving every year further back in time, closer to the moment when the first star ignited in the first galaxy in a universe that had been dark for 200 million years. We do not yet know what we will find when we finally see that moment. We do not know whether the first stars will look as expected or will surprise us the way everything else in the early universe has surprised us. We do not know whether the tension between Webb's observations and our models will resolve smoothly through refinements to galaxy formation physics, or whether it will deepen into something that requires a more fundamental rethinking of early cosmology. We do not know, and that not knowing is not a failure. It is the most exciting possible state for a science to be in. It means the universe still has things to tell us that we haven't heard yet. It means the next observation might change what we think we know. It means the work is not done. The questions are not answered. The frontier is not closed. The oldest light in the universe is 13.5 billion years old. And somewhere out there, waiting to be detected, is light that is even older. From the first stars, from the very moment of cosmic dawn, from the universe's most ancient chapter, the one we haven't read yet. We built the telescope. We know where to point it. We are looking. And here is the last thing I want to say. Not about the science, but about what the science means. There is something genuinely extraordinary about the act of looking at old light. Not just the technical achievement of building a mirror that can catch a photon after a 13.5 billion year journey. Not just the mathematics of computing a redshift and a look-back time with precision. Something more personal than that. Something that connects the act of observation to the nature of time in a way that I think deserves a moment of attention. When you look at the night sky, you're not seeing the sky as it is. You're seeing it as it was. The moon as it was 1.3 seconds ago. The sun as it was 8 minutes ago. The nearest star as it was 4 years ago. The Andromeda Galaxy as it was 2.5 million years ago. Before our species existed, before our genus existed. When our ancestors were small-brained hominins in Africa, whose world was bounded by the horizon and the sky they slept beneath. Every photon that enters your eye from a distant source is a time capsule. The night sky is not a present moment view of the universe. It is a layered archive of the past, with nearer objects representing more recent epochs and more distant objects representing progressively earlier ones. All of it arriving simultaneously at your retina, a superimposition of every moment from the recent past to the ancient past, displayed together as if they were contemporaneous. The Andromeda photons and the Milky Way photons that hit your eye at the same moment left their sources 2.5 million years apart. They share nothing except the accident of arriving at your eye simultaneously. James Webb Space Telescope extends this to its limit. The photons from JD's GSZ 14-0 that hit Webb's gold mirrors in 2024 left their source when the universe was 290 million years old. They were emitted by stars that no longer exist, in a galaxy that has since evolved beyond all recognition, in a universe that was nothing like the one those photons spent 13.5 billion years crossing. And yet they arrived. They crossed the expanding void. They survived the collision with dark matter halos, the gravitational lensing of intervening structures, the redshifting that stretched their wavelength to 14 times its original value. They arrived, and a piece of technology assembled by a species that has existed for 300,000 years caught them, read them, and decoded the message they carried. The message is, we were here. We formed early, faster than your models predicted, from gas that was more efficiently converted to stars than your simulations assumed. We enriched ourselves with oxygen before you expected us to. We were already on our second generation of stars when the light you're reading left us. We were here. And somewhere behind us, earlier still, were the ones who came before us. The truly first stars, the truly first light, in a galaxy or a cluster that we did not enrich but simply ignited from primordial gas. Find them. Read their message too. That is what the oldest light tells us. Not just when the universe started building structure. Not just how fast the first galaxies formed. But something deeper, that the universe has a history that is legible, that leaves evidence, that can be read by patient observers with good enough instruments. The universe is not indifferent to being understood. It leaves its autobiography, written in light, scattered in every direction, waiting across billions of years for someone to build a mirror large enough and cold enough and precise enough to catch it and read it. We built that mirror. The oldest light in the universe is 13.5 billion years old, and somewhere out there, waiting to be detected, is light that is even older, from the first stars, from the very moment of cosmic dawn, from the universe's most ancient chapter, the one we haven't read yet. We built the telescope. We know where to point it. We are looking.